All right. Let's do it. We can talk about liquids. Next state of matter to talk about. So just a reminder, right? The whole theory of atoms, the atomic nature of matter, everything's made up. Matter is made up of atoms, these tiny little things moving around, right? That's still underlying all of this stuff. So we talked about solids in the last lecture as well, and essentially that's where the atoms are pretty much confined to a specific shape, right? The solid will hold its shape, can stand up on its own, and that meaning that the atoms, it's not that they're not moving, they're just jiggling sort of in place. So liquids, again, they don't have a defined shape, meaning they'll conform to whatever container they're in, whatever space they're in, they want to fill up as much as possible. And also, similar to solids, liquids are, we would say, nearly compressible, meaning very tough time squeezing a liquid down. If you imagine, filling up a water bottle to the very brim with water and capping it off, and trying to squeeze that water bottle, you'll have a very difficult time doing anything more than just kind of a little bit of a tiny bit of a squeeze there. So the picture for liquids is that we have still atoms, right? But instead of, unlike the solids where the atoms are sort of in their defined structure and they just kind of jiggle around in place, for liquids, there's no defined structure. It's just, they're going all the way around. Which is why they can just sort of freely conform or form to whatever volume they're in. Right, so when we talked about solids, what sort of the defining property of a solid was its density. How dense is that solid? So the same idea holds for liquids, right? Liquids have a density too, and it's the exact same, calculated the exact same way. It's the mass of the liquid divided by the volume of that liquid, you get the density, right? So density is also an important property for liquids, but on top of that, we want to start thinking about a new property that comes up in liquids and then also in gases, which is pressure. So pressure is essentially a force that's applied over an area. So it's not just like, well, I can make different kinds of pressure by pushing my finger onto my palm as hard as I can. That's one amount of pressure because it's a certain amount of force that I'm exerting with my arm onto my palm all the way down that tiny little area of my finger, versus if I push my hand on my other hand, right? Same amount of force, I'm using my arm to push that force, but it's a much larger area now. So there's a difference in pressure in these two situations. And pressure, more exactly, is equal to the total amount of force being applied divided by the area that force is applied over. So in terms of proportionality, we would say the pressure applied is proportional to the amount of force that's being applied, and inversely proportional to the area that force is being applied over. If we were to look at the units for pressure, well, force we typically measure in newtons, and area we might measure in square meters. Say meter by meter is an area. So the metric unit for pressure is a newton per square meter, and we compact that all together and call that a Pascal. So a Pascal is exactly the same as a newton per square meter. And so as it turns out, the pressure of the atmosphere, atmospheric pressure, meaning the pressure of all the gas that's around us, all the air that's around us, pushes on us as a certain force, and it pushes over the area of our body, it pushes over everywhere. That pressure is about 100,000 pascals. So it's quite a lot of pressure. So let's just look at an example of calculating pressure in a fairly straightforward example. And that is if you have, say, like a rectangular brick gold brick, and it's resting on a tabletop, right? So that brick is going to be exerting a force downward on the tabletop, and there's an equal and opposite force coming back up, the support force. Don't worry about that, right? But hopefully you remember one of Newton's laws. Right, so the force is the weight of the brick that's pushing down on the tabletop, and the area is that bottom surface of the brick that's actually touching or in contact with the tabletop. So, what do we need? Well, if the brick is 12 kilograms, right? We weighed it, found out the mass of it is 12 kilograms. That multiplied by the acceleration of gravity, remember 10 meters per second, tells us that its weight is about approximately 120 newtons. Right? So that's the weight, that's the force of gravity that's pulling this brick down. So that's the force that the brick is exerting on the tabletop. The area that that force is being exerted over in terms of meters, so you measure the brick and it's 0.2 meters by 0.1 meter. So maybe yay big by yay big, right? So that's the surface area that that brick is pushing on the tabletop with, right? Multiply those two together, we get an area of 0.02 square meters. Multiply those, not multiply those two meters, not multiply, when you want to find the pressure, remember pressure is force divided by area that the force is exerted over. So the force was 120 newtons, divide that by the area, 0.02 square meters, we get 6,000 pascals. So this is the force, the pressure that that brick is exerting on the tabletop, right, over that area it's exerting it. And again, note that atmospheric pressure is quite a lot more than that still, right? So the pressure of the atmosphere itself is more than would be just this brick. But I think we'll talk more and more about, we'll talk a lot more about atmospheric pressure next time we talk about gases. Okay, so let's try just a couple of examples where we're not going to calculate an exact pressure, but I want you to just try to compare situations and understanding that pressure is proportional to the amount of force that's applied and inversely proportional to the area that that force is being applied over. Given that information, can we distinguish between situations to say which of these setups is exerting more pressure? Okay? So starting out with this top picture, we have sort of setup A versus setup B. All right, these are the same identical bricks, same mass, same weight. They're just sort of long rectangular bricks. One of them is laying down and one of them is on its end. So which of those is a greater pressure? And then also with the second setup, again, situation A versus situation B, which one is exerting a greater pressure on the tabletop? So take a second to answer those. Alright, so hopefully for this top setup, you said it was situation B, which is exerting a greater pressure. Right? Why is that? Well, like I said, they each weigh the same, so it's the same amount of force that they're putting down or exerting down on the tabletop, but situation B is exerting it over a much smaller area. It's over the sort of narrow side versus side in A, it's the long edge that's down there, right? So a greater area, well, larger denominator means a lower pressure, or smaller area, smaller denominator means a larger pressure. So that's how pressure being inversely proportional to the area that the force is being applied over. Then in this second situation, well, in setup A, you have three times as many bricks. So this is 3 times the force. Each of the bricks is still identical, same weight, same size. So you have 3 times the force being exerted, but it's actually being exerted over 3 times the area of situation B. So if you triple the force and you triple the area, the pressure is going to remain constant. So essentially you triple the force, so you triple the pressure, but then you also triple the area, so you cut the pressure in a third again. Right? So you're back to the same pressure. So each of these is actually representative of the same pressure being exerted on the tabletop. Alright, so one more example, or I guess two more setups here to see if we can distinguish which of these situations is a greater pressure being exerted. So again, on the top, compare situation A and situation B, and on the bottom, compare situation A and situation B. And again, these bricks are all meant to be the same size, same weight. Yeah. Alright, so in this top setup, hopefully you said B is the greater pressure. Right? And why? Well, each of these situations, A and B, is exerting force down on the table, but they're exerting it over the same area, alongside of that brick, but in the B's case, it's 3 times the force, because there's 3 bricks that are all laying on the same area, essentially. So you triple the force, and you have a greater pressure, actually triple the pressure, than you would in situation A. And finally, how about this bottom situation? Well, it turns out that B, again, is the greater pressure setup. And the reason being is we have the same amount of force being applied in both these situations, right? Because they're both 2 bricks, and the weight of those bricks is the force of gravity pulling down on them, pushing on the tabletop. It's just that in B's case, all of that force is exerted over that narrow side of the brick, right? Just that small area. So smaller area, same amount of force means a greater pressure. Versus A, that larger area, so lower pressure. Okay, so that was all with bricks and things laying on tabletops. So what does that mean in terms of liquids? Well, one way to think about it is that you can sort of imagine liquids as being like stacks of very, very thin sort of bricks, right? You're just stacking up a whole bunch of them or something, but they're all mobile, right? That's maybe not the greatest way of thinking about it, but in terms of what the pressure is and how the pressure changes as you move into a liquid, that's a pretty good way of thinking about it, because if we look at the situation on the left where we have these 3 bricks stacked up, well, we could ask what's the pressure in between each of the bricks, and finally at the last brick in the tabletop, right? Well, if we just look at the very top brick, there's no brick on top of that, so we would say that's kind of the 0 pressure area, though there is atmospheric pressure. But there's no apparent brick pushing down, right? So there's no apparent pressure pushing down right there, but you go down below that brick, and now there's a certain pressure because the weight of that brick is pushing down over that area that those bricks are in contact with. And it's just a certain amount of weight because the force of gravity on that one brick. Move down further below the next brick. Now we have the same area, right? Just the surfaces between those 2 bricks. But now you have 2 bricks stacked on top of each other. So same area, greater force means down here at that second level down is a higher pressure. So we went from a lower sort of pressure to a medium pressure, and if you go down again, then same thing happens. It's the same surface area of that brick that's in contact. So the area is the same, but now we've increased the pressure even more. So the same sort of idea works in liquids, in that the deeper you go into the liquid, essentially the more force, the more weight there is above you from the water that's above you, from the liquid that's above you in general. So the deeper and deeper you go into a liquid, the higher and higher pressure we get in that liquid. So, I mean, it's partially why if you've ever been swimming and you dive down into the pool, it can be somewhat painful if you don't know how to pop your ears or equalize the pressure in your ears, because the pressure gets greater and greater and starts pushing on your eardrum. So let's actually see an example of this, right? So we're going to see this cup, and the cup is going to have these three little spouts in it, and we'll be able to actually see that the pressure gets higher and higher and higher as you go deeper into the liquid, because when you take off, they have these little spouts, and there's maybe some corks or some stoppers in these spouts, but if you take those stoppers out and you allow the liquid, the pressure at that level in the liquid in order to push out the liquid, then the stream at the very bottom is going to shoot out the furthest because the pressure is the highest at that level in liquid. Then you go up a little bit more, the pressure is a bit less, so the stream doesn't shoot out quite as far. Finally, you go up to the very top, there's much less pressure, so the stream doesn't really go out that much at all. So let's check that out. So we have this fairly nice setup. And there you go. You can see the difference in pressure and how far out the bottom stream wants to shoot out versus the next stream up versus the next stream up. Okay. So another thing to hopefully drive home that in a liquid, the pressure at any given depth in the liquid is really due to the weight of the liquid above it, which is again why when you go deeper and deeper into a liquid, you get a higher and higher pressure. So we can really see that in this demonstration where you take a cup, poke some holes in the bottom of it, right? Fill it up with water, and if you're just holding it stationary, then the weight of that liquid is all pushing down. It's all getting pulled. It's all getting pushed down, pulled down by gravity. Right? And so the water is going to, or the liquid, whatever it is, usually it's water, but oftentimes we're going to use water in situations. But that pressure from the weight of the liquid above is pushes the water out of those holes in the bottom of the cup. Right? But as I told you before when we talked about gravity, if you release or if you drop something, or if something is in this state of free fall, you no longer feel weight. You're weightless, right? Assuming you hit some kind of terminal speed for a second. But essentially, once you release it, it's weightless, and so the liquid on the top is no longer going to push down the liquid on the bottom, which means there's no longer going to be a pressure difference between the top and the bottom, and the liquid doesn't get shut out anymore. It's a very strange thing, but this is just showing you that it's really the weight of the liquid pushing down from the top that it causes the pressure at the bottom. And when you drop it, when you put it into that weightless state, we no longer get the water spouting out. No, it didn't go so well. See if we can get it when it's a little better. So water spitting out, you drop it and the water stops spitting out anymore. Right? No more pressure to push the water out. Alright. So the fact that pressure in a liquid and in a gas technically, but we're talking about liquids now, that the pressure in a liquid increases as you move down into the liquid means that when you have objects that are three-dimensional and you put them into a liquid, there's a certain pressure on the top. Essentially that liquid is pushing down on the top. There's also a certain pressure from the bottom that's pushing up. So when we talk about pressure in a liquid or in a gas, it's not just pressure downward, right, or to the side. The pressure is to say that that's the amount of in a sense, force that's kind of exerting in all directions. Right? So the pressure in liquid is exerted inward, outward, up, down, left, right. The pressure is going in every direction. Right? And that pressure, again, is due to the weight of the liquid on top. So when we look at a three-dimensional object, like a rock or something, inside of a liquid, again, the top of that rock is at a certain depth in the liquid, so there's a certain pressure. The bottom of the rock is deeper, meaning there's a higher pressure underneath. So overall, essentially, there's a net amount of force that's pushing upwards on the rock, because there's the pressure exerting over a certain area down here, a smaller pressure exerting over the same area sort of up here. Then the net effect of that is essentially a force that pushes upward, just due to the fact that there's a larger pressure underneath than there is on top. Right? And that force is what we call the buoyant force, or buoyancy, or what amounts to buoyancy. So in this picture we have, in arrows indicating the pressure around this rock, and the larger arrows, so the larger arrows are indicating the pressure is greater down there, right? Pressure's lower up here, greater down there. And the other arrows we have are the weight, right? So that's the force of gravity pulling down on this rock, and the net effect of the difference in pressure from the top and the bottom is what's drawn as this buoyancy force, this arrow pushing upwards. And yeah, so to put that all together, essentially, if the weight of that object is larger than the buoyant force, then the object's going to sink, right? Because the net force on this object is going to be downwards. You have a larger force downwards than we do upwards, so the object sinks. Otherwise, it's going to float. Meaning if its weight is less than the buoyant force on that object, it's going to float. So in terms of that buoyant force, or buoyancy, the amount of that buoyant force only really depends on the size and the shape of the object. Right? Once an object is fully submerged into a liquid, then it's feeling some pressure above, it's feeling a greater pressure below, and the difference in that pressure amounts to a buoyant force upwards. As long as that thing stays the same shape, it doesn't matter how deeply you sink into the liquid, the buoyant force is really just a measure of, it really comes from the difference in pressure between the top and the bottom, and that difference is always going to be the same as long as the shape stays the same. So that is to say that so long as your object is already fully immersed, it can be up near the top of the liquid, it can be way down near the bottom of the liquid, the buoyant force for that object is always the same. So it doesn't depend on the depth that you are in the liquid. Even though the pressure is changing, it's really the difference in pressure. And that difference in pressure is the same because this object is the same size. So that kind of leads us, or buoyant force leads us to Archimedes Principle, which has to do with, I guess maybe you don't know. That's not a great thing to say. But so Archimedes Principle deals with you take objects and you submerge them in water. Right? So if you do that, then the object is going to displace a certain amount of water. Right? So like in this picture, we start out with a weight, it's hanging on a scale, and maybe it weighs 3 newtons. It's a mass, whatever, it's iron or something like that. So you stick it into water, a big thing of water that's filled to the brim already. So what happens is that physically, the volume of that weight, like I showed last time when figuring out the volume of a solid, that whatever volume that is, once you put it into the liquid, it's going to displace that same amount of water. And if the water is already filled up to the brim, then the water can't go anywhere else, but it spills out of this container here. So you stick that weight in, and now we have the situation where all the water that was displaced is pushed over to the side here. So that is to say, well, if we weigh the water that spilled out, that's 2 newtons. So the weight of the water, the weight of the liquid that was displaced, is equal to the buoyant force that's going to be on that object. So in this case, if it weighed 3 newtons to begin with, you submerge it in water, you displace 2 newtons worth of water, then essentially the buoyant force on that object is 2 newtons. So now our scale would weigh, well, 3 newtons pulling down still, but right, so that means essentially that whatever liquid is displaced by an object that you put in that liquid, whether or not the object floats or it sinks, the weight of the liquid that's displaced, that is equal to, that is the same amount as the buoyant force on that object. So if we sort of have a piece of wood floating in water, and imagine kind of like taking that wood out but not changing anything else, let the liquid just stay as it is for a second, then that chunk of liquid, that's the water that liquid that would displace, right? And the weight of that water is equal to the buoyant force on that piece of wood. Right? Essentially, the buoyant force is the force that would have been on the water in that position, right? That chunk of water that you displaced. All right. How about try this out? So if we start out with, say, 50 newtons of water, and you put in a 10 newton block of wood that's buoyant, such that the water was filled to the brim, so we get 10 newtons of water falling out. What's going to happen to the scale here? It's going to go up, it's going to go down, it's going to stay the same. All right, hopefully you said it stays the same, right? Number of ways to look at that, but again, this block is floating, so the buoyant force on it is equal to the water that it displaced, right? All the water it displaced, that 10 newtons of water is over here, the block is 10 newtons essentially, so it's only needs to displace that 10 newtons of water. Right? So our scale would still read 50 newtons. Okay, how about you have a similar setup, right? We still start out with that 50 newtons of water filled to the brim, but now we take a 30 newton block of petrified wood. So we put the petrified wood in, it's the same size as the wood block was before, but we put it in, it's not buoyant, it actually sinks. So what's going to happen to the scale in this case? Take a second. Well, since the petrified wood isn't buoyant, that means it weighs more than the liquid it's going to displace. So it still displaced that same, still displaced 10 newtons of water, but it actually weighs more than that 10 newtons of water displaced, which is why it's not buoyant. So the scale reading is actually going to go up. More weight overall on that scale now. Cool. So some other things that kind of follow from Archimedes Principle is, well, it's a little bit, it's one or two logical steps, but essentially if you talk about the weight of an object and the size of it compared to the weight of the water or the liquid it's displacing, it turns out you can make more general sort of statements about the density of things and whether or not they're going to be buoyant relative to each other. So, as it turns out, if you have a solid object, it will float if it's less dense than the liquid that you put it in. So like in this case we have a billiard ball, but it's sitting on mercury. So the billiard ball is about 4 grams per cubic centimeter. The mercury is 13.6 grams, it's over 3 times that density. meaning that the billiard ball is less dense than the mercury, so it's going to be buoyant, it's going to float in that mercury. And one way to understand that is that essentially the billiard ball, when you put it in, since it's so much it's less dense than the mercury, it only needs to displace a certain amount of the mercury. You can displace a bit of that mercury that's a smaller volume than the billiard ball itself. So it just displaces a little bit of that mercury, and the buoyant force is now enough that you've moved that bit of mercury that moved out. That's the buoyant force. So that force is enough to actually keep that billiard ball up. Alright, so knowing this, what might we say about the density of, say, diet versus a regular cola? And how that might relate to even density of water? This is more of a rhetorical question, so I'll just answer it. That is that, well, obviously the regular cola is more dense because it's sinking, it's not buoyant in water. And the diet cola is floating, meaning it's buoyant, it's less dense than the water. And that actually includes, like, now we're talking about combined objects where it's the density of the, sort of the average density of the cola and the can together. But soda cans are fairly light, so most of that material is the cola. And yeah, so so water is somewhere in between there, right? The cola is more dense than the water, but the diet cola is a little bit less dense than the water because it's floating there. Alright, so if you only think about purely the density of an object and whether or not it's going to float in a liquid, then it might be a little bit confusing as to why we could have these iron, big steel ships. So, you know, wood, making a ship, something that's supposed to float and traverse oceans and things like that, makes a lot of sense to make it out of wood because wood is already less dense than water. Wood is somewhere about half to 0.8 grams per cubic centimeter. Remember, water, sort of our standard, is 1 gram per cubic centimeter. So the wood's less dense than the water. A wood ship, it makes sense it's going to float. But if you think about an iron ship, iron is almost 8 times the density of water. So how is it that this iron ship, this battleship, could float? Well, it still comes down to density, but we got to expand our idea a little bit. So just like when I was talking about the cans in the liquid, you have the cola, you have the diet cola, but the object itself, each of those is the cola and the can. And the can is mostly aluminum, so yeah, so when I mentioned briefly that the density of that can and the liquid is actually still, in the diet case, it's less dense still than the water, and the cola is still more dense than the water. So that was, in a way, a brief introduction to this, which we were thinking about as not just the pure density of a material, but now the average density of an object overall. So that object can be made up of multiple materials. So just as density for material is the mass of that material divided by the volume of that material, average density of any object is going to be the total mass of that object divided by the total volume that that object takes up. So now we can talk about, again, like combined materials, like objects that are made up of all kinds of materials. But if you take the total mass, you divide it by the total volume of that material, or whatever that object is, there you go, that's the average density of that material. And as it turns out, if you have an object and its average density is less than the density of the liquid, then Archimedes' principle still holds. It says that that object's going to float in the liquid. So in practice then, if you took a solid ball of iron, say that at a volume of 100 cubic centimeters and a mass of 790 grams, right? Divide that mass by the volume, the density is just the density of iron. It's 7.9 grams per cubic centimeter. Fine, cool. That's much more dense than water, so if you put that ball of iron into water, it's going to sink. However, if we somehow forged that iron or casted it in some way so that it's not a solid sphere of iron, it's a ball of iron or a sphere of iron, but it's hollow. So the same amount of iron, still 790 grams of iron, but it now has this air in the center, which expands the total volume out to be 1,000 cubic centimeters. So now 790 grams divided by 1,000 cubic centimeters, we now have a density, an average density of 0.79 grams per cubic centimeter. This is now less than the density of water. Right? Density of water is 1 gram per cubic centimeter. So this object is going to float in water. And this is in general how steel ships float, because the steel makes up the sort of the structure of the ship, but the volume of the ship is actually largely air. Mostly air. So yeah, so you get a steel structure or a steel frame of the ship that does something like that, where now the volume that's in that water there, again, is still less, the density of it on average is less than the density of the water, so it floats. Also another way of understanding that if you start getting water into that, if you have a leak in your boat, then the average density of your object is now changing. It's now getting denser and denser as the water comes in to replace the air. So that's why you don't want to have water in your boat, or else it's going to sink. Cool. So just keep kind of extending Archimedes Principle a little more. It turns out that the denser a liquid is, the consequence of that density is that it's going to have a greater buoyant force on any object that you place in that liquid. So, yeah, so for instance, if you try to float in a regular pool in fresh water, it can be difficult to float because your body is largely made up of water, but it's also made up of other things that are denser than water. Bone and muscle, things like that. So, depending on your exact situation, it might be difficult to float in fresh water. However, if you try to float in, say, the Great Salt Lake in Utah, it's pretty easy, because it's called the Great Salt Lake for a reason. There's a lot of salt in that water, right? And the salt actually increases the density of the water, so salt water is more dense than fresh water. So more dense liquid means a larger buoyant force, which means it's going to be easier to float. It's also the same reason why it's easier to float in the ocean than it is in a lake. Right? The ocean is salt water, more dense, it has a larger buoyant force on it. Okay, so the last point to make is just something kind of maybe connecting to the next lecture, but also just to point out that we talked about solids, and solids are things that hold their shape. They have a particular structure to them that doesn't really change unless you start changing the phase of it. But as long as it's in its solid structure, then it's going to stay in that whatever shape it sort of is. But now we're talking about liquids, where liquids just take the shape of any container that they're in. Right? A liquid is actually an example of a broader category, well, maybe more of a mechanics or kinematics sort of category that we call fluids. Right? The way that some materials can actually flow. They can move around in all these freely kind of moving ways. So liquid is an example of a fluid because it flows. It's just like the way it sounds. It turns out that gases and plasmas are actually very similar to gases. Gases and plasmas and liquids are all examples of fluids because they can freely flow through different volumes. They can expand, take up different volumes, so they continuously can change their shape There's no set shape to them. So yeah, so you have the example of like water or gas, like a cloud, or plasma, like lightning. All those are examples of what we call fluids. So liquids and gases, in a sense, are much more similar than solids are to either of those things. Yeah. I think that is it for this lecture on liquids now. So, right, mostly to do with pressure, talking about the pressure inside of a liquid, and then also talking about the density of a liquid and how that affects the buoyant force on objects, and objects are going to float or sink in those liquids. So yeah, that's it. Have a good night, or a good morning, or just a good day in general, and I'll see you next time.